Let's consider another reaction. In this one, we'll see that the rate law that was determined experimental, there we go, rate law is K NO squared BR2. Hooray, we're done. Just kidding. That's a termolecular reaction that we have there. 2 molecules of nitrogen monoxide and 1 molecule of bromine. Not going to happen. Remember, termolecular reactions don't happen. They are so implausible that we can't rely upon them as overall can't rely upon them as elementary steps. They're really more suited only for overall reactions. But our rate law agrees with this. But we know that we can't have a termolecular reaction, which means something weird is going on. And so let's consider the following. What if we were presented with 2 steps? We have a molecule of NO plus 1 of Br2 turning into NOBr2. And in step 2, we had an NO plus the NOBr2 intermediate turning into the 2 NOBRs that we had. And if we did combine these, we would see, indeed, we would have that intermediate of the NOBr2 and everything would cancel out. So we'd be okay in terms of overall reaction. But if we look at the rate laws, we would see that this would be, I'm just going to write it, K NO Br2. And this would be K NO times NOBr2. And neither of these is correct, as written, right? So first step isn't the slow step, because that doesn't agree with our experimental rate law. But the second step, we have an intermediate here. That's not something we usually see. And so what we might consider is how might we substitute that in? If we presume that the first step is fast and reversible, we can describe the concentration of NOBr2 if we're assuming that step 2 is the slow step, that, once it's around, it'll go ahead and react when it feels like it. But we have to also consider that the NOBr2 is also breaking down, right, if it's reversible. So we've got competing pathways here. So if step 1 is fast and reversible, we have 2 things happening here. We have the as written equation, and that has a particular rate constant. However, if it's reversible, if the reaction is also going in reverse, then we know that this is going to be breaking down again into the original components. And we'll say K minus 1 for this one, because it's essentially the reverse process, so we'll just put a minus 1 on it to indicate as such. And so if we want to think, okay, well, what if we substitute in this NOBr2 thing? As we know, it's breaking down, presumably as it's a reversible reaction. And so if we want to substitute that in, well, we know that the NOBr2, again, is formed from the NO and Br2. So why don't we combine those? By looking at their relative rates. If we compare them to each other, we know that the rate of NOBr2 production will be equal to the rate of depletion of the nitrogen and the bromine going away, right? So we know that the rate of NOBr2 consumption is going to be related by including their rate constants. So we know that we have the rate of production of NOBr would be K minus 1, sorry. We have K1 of NO and Br2, right? These are just stoichiometric, right? We know that the rate of breaking down and forming would just be the same as each other, because this is a fast reversible reaction. I'm sorry, I've forgotten my brackets here. And this is the weird part. If we solve this equation for NOBr2, the concentration of which, we can get a term that we can substitute in. It's bizarre, but it's simply the reverse reaction that we're looking at. So we're looking at K minus 1 times concentration of NOBr, and since this is a fast reversible reaction, we're suggesting that those rates would be the same. The rate of production and the rate of going away is the same. So we can substitute it in with something we do know. We can calculate the rate for K1. We can calculate that experimentally. And so if we do this bizarre thing of combining the like terms, or rather getting it so we can substitute in, we can now go to our original projected elementary rate law, which was that rate equals K times NO, or K2 we can say, times NOBr2, remembering that we can't use an intermediate in a rate law because we don't have it experimentally. If we just plug this in, all of this value goes right here. If we plug that in, we get the following. K2 times K1 over K minus 1 times the original NO times NO times Br2. And if we combine them, we can get rid of all this crap and just put a new K. Because remember, it's just a rate constant. We don't actually need that for describing the rate law. And if we combine these two, that's NO squared times Br2, Br rate. This is a bizarre way to look at it, but when we're looking at slow second steps, we can describe it in terms of looking at the original reactants as well. So we're including both the original reactants and how they're making their intermediate, as well as the reactants in the second step, the slow step. And by doing so, we can end up with the following rate law. And indeed, this is the one that was experimentally determined. And so this suggests that we have a fast reversible first step and a slow second step. And so with this, again, bizarre scenario, we end up we're able to kind of take our knowledge of rates and rates constants, putting them together, we can substitute in for our intermediate concentration. It's the ratio of the rates of the forward and reverse reactions and the initial, or the concentration of our initial reactants for step 1. Once we plug those in, we get a mess of rate constants, but thankfully, since a rate law, we just put the term K anyway, we can just combine all of those into just a new K, whatever it may be. And then we'll end up with that rate law. And so that's how we can get a reaction mechanism that includes only bimolecular steps to have a rate law that appears termolecular. So remember, termolecular reactions don't really happen. They don't really happen. So in order to see them experimentally, we must have other things going on. And in this case, we're looking at something with a fast reversible first step and a slow second step. In our final and kind of section of this chapter, we're going to look at catalysis. What are catalysts and how do they work?